Okay, continuing with our introduction. We want to give an example of an algorithm that in fact requires a bit of mathematics, both to prove that it terminates in a reasonable number of steps and that it produces the desired solution. And this is the famous stable matching problem. So, assume that you are running a dating agency and you have n men and n women as customers. So they all attend a dinner party and get to know each other. And after the party, every man gives you a list with his ranking of all women present, from the one that he finds the most attractive, and then in decreasing order of his preference. And every woman gives you the list of her rankings of all men present. Your task is to design an algorithm which produces a stable matching, which is a matching of pairs of men and women, which satisfies the following property. It never happens that for two pairs, P equals a man M and woman W, and P prime, which is a man M prime and woman W prime, it never happens that man M prefers the other woman W prime to the woman that he is matched with, woman W. And that woman W prime prefers M to the man she is matched with, M prime. So it's never the case that M likes better another woman than the woman he is paired with, and that woman in fact likes him better than the man that she is paired with. So here is an example. The arrows in this picture indicate the preferences. So this is just with two pairs. And the arrow from man M1 to woman W1 means that M1 prefers W1 to W2. And for example, the arrow from W2 to M1 indicates that she prefers M1 to man M2. One can easily verify that this produces a stable matching when M1 is paired with W1 and M2 is paired with W2. Why is this so? Well, man M2 prefers W2 to the woman he is matched with, but that woman doesn't prefer him to the man she is matched with. She prefers the man she is matched with. On the other hand, on the right you can see an example of a matching that is not stable. Why? Because M1 is matched with W2, but M1 prefers W1 to W2, and W1 prefers M1 to the man that she is matched with here. So this is an example of a matching that is not stable. Another example is with preferences indicated as here. And interestingly enough, there are two stable matchings. Both matching M1 with W1 and M2 with W2 is stable, as is matching M1 with W2 and M2 with W1. You can just verify that in both cases the two conditions of the condition for stable matching is satisfied. So sometimes there can be several stable matchings. But we should first see whether working towards the solution of existence of stable matching, it's easy to verify that in case of just two pairs, no matter what preferences, there is always a stable matching. So the cases are that either two men like two different women, or two women like two different men. In this case, it's easy to see that this is a stable matching. And the second case is if both two men like the same woman and two women like the same man, it's easy to see that in this case also a stable matching exists. Just go through the conditions and verify that the matchings are stable. So the question is it true that for every possible collection of n lists of preferences provided by all men and n lists of preferences provided by all women, a stable matching always exists? This is not trivial to common sense that something like that should always exist, regardless of the ordering of men and women on the corresponding lists, right? The answer is yes, the stable matching always exists, but this is not obvious. Now let's see, given n men and n women, how many ways are there to match them, i.e. to form n couples, right? And the answer is n factorial. To see that, you can simply order men 1, 2, 3, up to n. And now any placement of women, 2, 5, pi, and permutation. So any permutation will do. So this means that the total number of pairings is exactly equal to the number you can permute n women here, so n factorial. And n factorial, if you use Stirling formula, grows faster than the exponential, or faster than 2 to the n. In fact, it's approximately n divided by e, when e is the Euler constant, 2.71 and so forth. So n divided by e to power n, and this grows significantly faster than 2 to the power n. So if you tried by brute force to find a stable matching, the algorithm will be prohibitively slow, because the number of cases that you have to test is huge. So the question now is, can we find a stable matching in a reasonable amount of time? And the answer is yes, using the Gale-Shapley algorithm. Now, the algorithm was not invented for any dating agency needs, but in fact it was invented to pair newly graduated physicians in the United States with hospitals for residency training. So each physician would submit a ranking of all hospitals in the order of his preference where he would like to go to do his residence training. And each hospital would make a ranking of all physicians that they would like to have, and then Gale-Shapley algorithm produces a stable matching that places the physicians into hospitals. Notice, in this case, of course, number of newly graduated physicians is larger than the number of hospitals, so it's not n men and n women to be matched, but for simplicity we will consider just the case with when the number of men is equal to the number of women. So, how does the algorithm work? It produces pairs in stages with possible revisions. A man who has not been paired with a woman will be called free and happy man. Men will be proposing to women, and women will decide if they accept a proposal or not. We start with all men free, and then, while there exists a free man who has not proposed to all women, we pick any such free man, M, and have him propose to the highest ranking woman, W, on his list, to whom he has not proposed yet. So notice this ensures that every man can propose to a woman only once, because each time he proposes to the highest ranking woman that he hasn't already proposed. If no one has proposed to W yet, she always accepts and a pair MW is formed. Else, if she is already in a pair P' with some man M', then if M is higher on her list of preferences than the man M' that she is paired with, then the old pair, when woman W is paired with man M', is deleted, M' becomes a free man, and a new pair of woman W with the proposing man M is formed. Else, if M, the proposing man, is lower on her preferences than M', then the proposal is rejected and M remains free. Now, to see that this algorithm works and that it terminates in a reasonable amount of time, we will prove several claims. So first claim is that this algorithm terminates after at most n squared rounds of the while loop. Why is this so? In every round of the while loop, one man proposes to one woman. Every man can propose to a woman at most once, because a man always proposes to the highest ranking woman that he hasn't already proposed. Thus, every man can make at most n proposals. There are n men, so in total they can make at most n squared proposals, which means that the while loop can take at most n squared many rounds. The next claim is that algorithm produces a matching, i.e., that every man is eventually paired with a woman, and thus also every woman is paired to a man. Why is this so? Well, the proof is simple. Assume that the while loop has terminated, but M is still free. This means that M has already proposed to every woman. Otherwise, if there is a woman he hasn't proposed, the while loop can make an extra step. So M has already proposed to every woman. But a woman always accepts a proposal if she is not paired with anyone. So since M has proposed to every woman must be already paired. But this means that every woman is paired with a man, because A woman is not paired with anyone only if no one has made a proposal to her. But we just assume that M has already proposed to every woman, including that woman. So every woman is already paired with a man. But this is not possible because there are n women and n men. So if every woman is paired with a man, all of the men are also involved in pairs, which is contradiction with our assumption that M is still free. Either next claim, we want to show that matching produced by algorithm is stable, which is not clear from just the definition of the algorithm. So let's see how we prove that. During the while loop, a woman is paired with men of increasing ranks on her list because she always accepts a proposal from a man if she is either free or already paired with someone who is lower on her list of preferences. So women will be paired with men in increasing ranks on her list. A man, on the other hand, is paired with women of decreasing ranks on his list because he always proposes to the highest ranking woman that he hasn't proposed yet. So now assume the opposite, that the matching is not stable. So what does this mean? There are two pairs, P equals MW and P prime equals M prime W, such that M prefers W prime over W and W prime prefers M over M prime. Since M prefers W prime over W, he must have proposed to W before proposing to W prime before proposing to W, because he always proposes in the order of his preferences. Since he is paired with W, woman W prime must have either rejected him because she was already with someone whom she prefers, or she accepted his offer but later dropped him after a proposal from someone whom she prefers. In both cases, she ends up with a man M prime whom she prefers over M, which is a contradiction. After each segment, and we have just finished introduction part for this course, I will be giving you a puzzle. And these puzzles are integral part of the course. You will not be asked to solve puzzles on your exams, but solving puzzles is an excellent way of training your problem-solving abilities. So always try to solve the puzzle for the lesson. So here is the first one. So Tom and his wife went to a party where 9 more couples were present. Not everyone knew everyone else, so people who did not know each other introduced themselves and shook hands. People who knew each other from before did not shake hands. Later that evening, Tom got bored, so he walked around and asked all other guests, including his wife, how many hands they had shaken that evening, and got 19 different answers. You have to find out how many hands did his wife shake and how many hands did he shake. So this is a beautiful puzzle because prima facie there is no connection between the information that you are presented, that he got 19 different answers asking 19 people present beside himself at the party, and a number of handshakes that Mary had, but this is in fact not the case. So a little hint is, look at the people that shook the largest possible number of hands. And that's all for introduction.